Welcome back, everybody, again. So that last lecture was definitely not 5 to 10 minutes, so that is my bad. But this one, fear not, is not going to be that long, mostly because it's review, so that's cool. Let's get started. Play from current side. So lecture 21 is all about mountain building. Okay, so we talked about mountain building quite a bit already, right? And as you all know, most of our highest mountains in the world are attributed to what plate boundary? Okay, and if you're all screaming from your living rooms, conversion plate boundaries, you would be absolutely right. This is where we create our mountains. Okay, so this lecture is really less about where they're occurring on the globe, right? Convergent versus divergent versus transform. And it's more about looking at what these mountains look like in cross section, or what do their faults and their folds look like, okay? Because remember, we have thrust faults or reverse faults, and we have folds happening in convergent settings, in collisional settings, right? So what do those look like in mountains? Okay, so I'm going to flip through these. You can also go through this again on your own time. Okay, I just want to get to the meat of it. Okay, and before I get there, let's talk about topography. Okay, and so topography seems kind of self-explanatory. I'm sure you all know what topography is in some extent, but as a good refresher, it's the record of the elevation of an area. Okay, so we talk about high topography and low topography, right? High topography would be, of course, where our Himalayan mountains are, our high mountains, our high topography. Our low topography would be our rivers and our valleys. Even lower topography would be our trenches in the middle of the ocean. Okay, so how tall landform is in elevation, how low it is. And topography also records the slope of something. So, for example, these Himalayan mountains have a pretty steep slope to them. Okay, whereas maybe these hills lower in this bottom diagram would have a gentle slope. So the difference between a really steep mountain versus a gentle hill slope. Okay, or a canyon versus a mountain. Okay, canyons are very steep, mountains can be very steep, but we have landforms that are a lot gentler. Okay, so that is topography in a nutshell. Okay, so we talked about convergent plate boundaries and how these are going to be where our big mountains are being formed. Okay, so these are our compressional settings, right? You're creating our folds and we're creating our thrusts. So a lot of times when we talk about mountain building, we have our fold and thrust belts. Okay, this is where we have our folds from our ductile deformation existing in the same places or in the same neighborhoods that we would have our thrust belts. Okay, so remember the same type of stress. It's just going to be the difference between brittle or ductile deformation. So maybe one is happening a little bit deeper in the crust and one is happening a little bit shallower. Okay, but they're both related to compression. Exotic terrains is something that we're going to talk about a little bit more when we talk about Earth history. And they consist of island fragments of continental crust that had its own geologic history. And then these islands were smashed onto another continent. Okay, so you can think of, we're going to talk about North America and how it formed quite a bit. But North America isn't actually a bunch of island arcs that were smashed onto each other over time. Okay, so these were terrains or exotic terrains that had their own geologic history. So maybe they formed through subduction zones, or maybe they formed through a hot spot. And then they traveled across the globe via plate tectonics, and then they ended up smashing into another continent and sticking onto that continent. Okay, that's an exotic accreted terrain. Okay, so let's keep moving on. Keep it going. Okay, and so here's a nice cross section of a fold and thrust belt in a continental collision, right? We have our nice folds that were formed ductily because maybe it was hotter, it was at a higher temperature. And then we also have the faults. Okay, usually you have faults that are separating these faults out. Okay, so you can see the outline of this fault right through here. And then we have these folds forming nice and ductily in this really high pressure collision zone right here in the center of the collision. Okay, so this is what it looks like in cross section. Okay, here's a really nice diagram showing this again. Okay, you have our thrusts, faults that are forming on the edge of this continental collision, and then you have this nice fold deformation happening right in the center of the mountain belt. Okay, so you also get some topography in continental rifts. I wouldn't really call these huge mountains really high topography, but you do get some variation in topography in continental rifts. And the biggest reason for that is because when you have continental rifting, you're stretching and thinning the crust like so, right? You're stretching and you're thinning the crust, and that crust is getting really, really thin. While on the edges of that thinning, right, you still have continental margins, right? So in this diagram shows it really nicely. You're thinning the crust right in the center, and again, this is a continental rift, right? So this is a rift that's happening in the middle of a continent, not quite the ocean. Okay, you're going to have these margins on the edges of this rift center, and these are going to be where your continents are, your continental crust is, for example, right? They're going to be a little bit thicker than this thinned section here in the middle, right? So you're going to create relative to our thinned portion in the center, you're going to create some mountain structure, some higher topography relative to our thinned crust where we're rifting. Okay, you'll also get some rift volcanoes right in the center. Okay, that's also going to create some topography differences in that region. But when we talk about these big mountains, these big, high, tall volcanoes, usually, without a doubt, they're going to be in these continental collision zones. Okay, but you will get some difference of topography in rifts, just not as great as our big mountains. Okay, so why are mountains so high? We explored this when we looked at Lab 1 back in the day, all those many moons ago when life was simpler. So revisit this slide. Okay, and then wrapping it up, what goes up must come down. So our highest mountains in the world are really, really high, but that doesn't last forever. Okay, because over time, what happens to mountains? They get eroded and they get weathered over time. So wind, water, rain, glaciers, they like to break down rocks, right? Gravity also likes to break down rocks. Okay, you build up mountains really high, gravity is going to want to pull them back down to the center of the earth. So mountains reflect a balance between uplift and erosion. The taller the mountains get, the more that they erode, okay, because what comes up must come down. Okay, so when tectonic uplift or our mountain building event slows, the mountains are reduced in elevation, so they are eventually eroded back to sea level. Okay, and this is a very prevalent story in the Appalachian Mountains, which we've talked about quite a bit throughout lectures, right? The Appalachian Mountains were these really tall, ridiculously tall mountains on the northeast portion of North America. As we know today, hopefully, there aren't these really huge mountains anymore where we are. Why is this? Because of erosion. Okay, the erosion events of the Appalachian Mountains over millions and millions and millions of years wore these mountains down, broke them down, and reduced them to really just gentle hills, if anything, instead of these great majestic mountains that they once were. So I have a couple of time slices of the Appalachian Mountains and how they formed through time. Okay, so go through these on your own time. Starting off with this Grenville orogeny, and this is a mountain building event about 1 billion years ago. Okay, and then after some millions of years ago, that Grenville orogeny rifted and started to separate. It extended, created a passive margin. Okay, and now we're going to get an exotic terrain smashing into that passive margin. Okay, so this little island arc is now being subducted. That subduction zone is going to get smaller and smaller and smaller, and that exotic terrain is going to move closer and closer and closer to that passive margin. Okay, and eventually that island arc is going to smash in and get stuck onto that continent. Okay, and so this is what happens with the Appalachian Mountains. It accretes all of these exotic terrains, right? all of these islands smash into the continent, building these mountains higher and higher. And each time that an exotic terrain gets smushed on to the continent, the mountains grow taller, and you grow North America not only in height, right, but you also grow North America spatially. Okay, so you're going to grow it in size as well. You're going to keep growing the continental crust. Okay, and so here's a couple of more collisions. The last collision event that the Appalachians experience is the collision with Africa, when we have the formation of Pangaea, our last great supercontinent on the globe, right? So Africa came, smashed into North America, created the Alleghanian orogeny, okay, and that was our last big mountain tectonic building event that we have in the Appalachians. The last tectonic activity to happen to the Appalachian is this Mesozoic rifting. Okay, so Pangaea formed our supercontinent. Over a few million years, it decides that it doesn't want to be with each other anymore, so now we get rifting. Okay, so the continent is now being pulled apart. Okay, and then this is what present day looks like. The same type of story happens to Massachusetts, believe it or not. Okay, so Massachusetts experiences the same type of tectonic events that the Appalachian Mountains experience, more or less. Okay, so I made these little diagrams here. So go through this on your own time and see how Massachusetts grows through time. So it starts off as this little sliver, right? Maybe the rest of this continent in Laurentia or other parts of North America. And Massachusetts is just right on the edge of this ancient continent called Laurentia, and then it grows through time. Okay, and each time an island arc gets accreted onto North America, Massachusetts grows a little bit more, with the last event that we see being this rifting event. So now the continent's being pulled apart. Okay, and so this is where Springfield is born. Okay, and this is where we have our Springfield. So Springfield is actually in the middle of a rift basin. Okay, so that's really cool. And that's a little tectonic history of Massachusetts. So that is pretty much the end of this lecture. Watch the videos, watch the YouTubes, and stay tuned for the next one.